Hi, my name is Annika Patka, and this is my Lab 3 for my Physics 1 class at Georgia Tech. This lab asks me to analyze the motion and forces upon a star to find the unknown mass of a black hole. To do so, I use Newton's second law, also known as the momentum principle, as well as the gravitational force to determine this unknown mass. It is important to note that the star is actually the system in this lab and that the black hole is included in the surroundings. I've included the graph of the star's motion around the black hole as well as the results from my code. The results from my code show the mass of the black hole as well as the net force and its parallel and perpendicular components. Before working on the physics components of this lab, I had to designate a few initial conditions. While I didn't change the value of the universal gravitational constant, I thought it was important to mention it early on in the report because it'll be used in further calculations. I had to update the mass of the star to match the one given in the instructions of the lab. The last initial condition I had to set was the time interval. I simply converted the hours in a day to seconds, which left me with 86,400 seconds. The calculations on this slide are pretty simple. Since momentum is defined by mass times velocity, I simply took the initial velocity and the final velocity to create initial and final momentums. Since the change in any quantity is simply the final quantity minus the initial quantity, I applied these principles to create my delta V and delta P. To get the rate of change of momentum, or dP dt, I simply divided my delta P value by my delta T, which is also equivalent to the net force as seen in my derivations to the right. In the top right-hand corner, I show the equation for a unit vector, which I apply to get my p hat unit vector for momentum. However, things get a little more complicated when we talk about the parallel and perpendicular components of the rate of change of momentum. For you to really understand where my values came from, I wanted to include my derivation process. I start with the value of momentum being equivalent to the unit vector times the magnitude of the momentum. From this equation, I apply the derivation product rule, which gives me the equation below. On the right side of the equation, we see the separated parallel and perpendicular components. From this, we find that the parallel component is essentially equivalent to the unit vector multiplied by the magnitude of dP dt. As you can see in the third line, that's exactly what I did to get the parallel component. Since I now had the parallel component, finding the perpendicular component was easy because I could simply subtract the parallel from the entire value to get the perpendicular component, which is what is done in the fifth line of the code. Additionally, since the parallel and perpendicular components of both the net force and the rate of change of momentum had the same magnitude, I was able to set these values equal to each other as seen above. Later in my report, I'll explain what each of these components mean. Finally, with each of these values, I was able to solve for the mass of the black hole. The process of finding the mass of the black hole was actually quite simple because I had all of the other values in the equation for gravitational force except for this mass. When I created the variable for the mass of the black hole, I simply applied the variables in GlowScript to the equation I had found, which gave me the value of 1.55 times 10 to the 34 kilograms. One of the questions that this lab asks is that if we change the mass of the black hole, but nothing else about this problem, including the motion and the position, would we be able to find this new mass? And in terms of the model that I have created, I would not be able to find the new mass. This is all due to the fact that if the motion and position are unchanged, the net force and the radius would also be unchanged in the equation that I have. Due to the fact that these quantities, as well as the gravitational constant and the mass of the star would be the same, there would be nothing else in the equation to give us a different value. Finally, this lab also asks the differences between the net force components and the rate of change of momentum components. While the magnitudes of each of these corresponding components are the same, these quantities do mean different things. For example, the net force in the parallel direction describes the net force as parallel to the motion. However, the rate of the change of momentum describes the change in magnitude of the speed of the object. Similarly, the net force in the perpendicular direction describes the net force is perpendicular to the motion of the object, whereas the rate of change of momentum in the perpendicular direction describes the non-parallel change in direction of the object.